little bit. So basically, I'm going to go back on the blackboard in a moment, but I want to go through and review where we are. So basically what we've been doing is governor response. That's called primary control. And I'll explain what secondary and tertiary control are. And it goes on and on and on. I mean, there are so many terms here, and they mean different things in different parts of the country. Just a little bit about the need for the secondary control, just to motivate the lectures that come. Okay, so again, this is something I thought before and I didn't explain, and I went back to look at it, and it's a good thing. I mean, there's no way to explain this, because it's a particular paper on how to deal with wind farms. And, you know, everyone says because of a lack of inertia, which gives you that M that we've been talking about. I'll review that in a moment. Because of a lack of inertia, when you have a lot of wind and solar, you have a lot more swings in frequency when there's a disaster. So these are simulations where there's a generator outage at a certain time, and with different control swings, techniques, you get different swings in frequency. You know, and so without any auxiliary control, well, that's some control that they're promoting for this. You'll get one particular swing, and with their synthetic droop at the wind turbine level or the wind farm level, they brag about how they can reduce that swing downwards. And damn right, you know, I'm sure that they can do a good job with that. You know, you need some sort of way you need actuation to do it. You know, with a governor, you know what it is. You can turn a valve and supply more or less mechanical power. With a wind farm, there's no valve. So what the hell do you do? So over the next month, we'll try to problem solve that question. You know, what do you do when you don't have a resource like a valve you can turn? And batteries are going to be one thing, but we'll do better than batteries. And forget inertia control and all that. So anyway, if you want to read about this, you can link this, but there are a million papers like this trying to deal with these wild frequency swings anticipated when you have less inertia in the grid. All right. You know, so I've given you, I don't know why I'm repeating this, but I mean, you know, we're ignoring when we came up with our power grid model last time, we're ignoring the huge transmission dynamics and losses and all of that. And we ignored the fact that there's some gigantic regions like the entire Northeast, or I mean, and much smaller regions like ERCOT. ERCOT's islanded completely, you know, a Texas thing. Yeah, Texas is one interconnected system. Interesting, Quebec is like Texas. You know, it's islanded itself off from the rest of the world, although there are DC tie lines and all. But this is a thing that, you know, this is what we've been talking about the last lecture, is that each generator works together, looks at local measurements to stabilize the grid. And so you've got this distributed control problem. And as I've said, there's no science for that. So you can't pick up a book on distributed control and learn anything, because there are no results. There's nothing. There are a bunch of counterexamples, a bunch of results saying you can't optimize. You know, there's no the complexity of computing an optimal solution based on distributed architecture is exponential, you know, things like that, you know, or NP complete, you know. But there's no theory at all. So that's what's really cool. I mean, so just by trial and error and monkeying around, power engineers have come up with this incredibly robust architecture, and we're just starting to see how some explanations of why it works. Now, so this is a steady state analysis, which I wanted to draw a picture earlier, but you know, we've got I flip this around. I mean, normally you have frequency on this axis and power on this axis, but it doesn't matter. When you have these decreasing plots, because when the frequency, so that's the nominal frequency. If it goes down, then the power from the generator in steady state goes up. So if the frequency stayed at omega 1, generator A would, based on its nominal, would boost up its power a lot because it's got a larger droop gain. The slope there has to do with the droop gain. And there's an offset as well. So this droop characteristic, the slope, determines the share of primary control delivered by the generator, and they're pretty much all the same. Those slopes are all the same relative to their percentage of the percentage of power, you know. So in response to a hypothetical 1 degree drop in frequency, if that's absurd, say 0.01 degree drop in frequency, percentage-wise, they all give the same share. And that's what's meant by a 5% droop, you know. So, and NERC demands, I saw, they've even made a bigger alert this year. So last year they were screaming about no more than 6%, 5% is good. They're worried about this because the dynamics of the grid are depending on that. I mean, this is not because of steady state analysis. This is because it's this distributed control problem, and they're scared because they don't, you know, we don't have any theory for this. You know, I mean, that you can see bad things happen, and you say, hell, our droop gains are too big or too small. No. Okay, so what we end up with is first of all, we're going to keep on talking about primary control a bit longer. We're almost done with that. And primary control is all about the beginning, you know, about trying to avoid crazy swings like this in frequency. So this is it. I mean, India has the best plots because it's allowed to be more relaxed. The frequencies vary more. And also there's a wonderful resource. You can find it on the website. IIT Bombay has all sorts of beautiful plots of disasters, just wonderful plots, which are hard to find in other parts of the world. They happen everywhere, but it's just India is very nice about sharing it. And IIT Bombay is the best power group in the country, in the world, I mean, not the country, in the world. In India for sure, and in the world. In terms of people hours, I mean, they have incredible people working on and who really care about that $500 billion. Did I mention this in the lecture? That India went, Arun's lecture, Arun Majumdar's lecture, he mentioned that India wants to spend $500 billion on renewable energy, and IIT Bombay is going to get a good percentage of that money, I'm sure, for research. So they're building big indigenous solar power plants so they can avoid buying solar panels from China, things like that. So anyway, so basically this is just the kind of things you see. So this is sort of, and again from India, where you see some crazy deviations in frequency, that might be measurement error, and the frequency going downwards, this is the kind of thing you'd expect from just primary control. Because remember, the steady state analysis said that if with just primary control, if there's a increase in load or a drop in generation, this would be from a generator dropping out, the frequency will reach some steady state, and it'll be some new value. So if you lose a generator, the frequency will converge to some steady state. This is the reason you need secondary control. I think that's what I say here. No, that's not what I say here. But the fact that you don't get restored to the nominal frequency, in this case, well, this is not 50 hertz. Eventually 50 hertz is because this is before the secondary control is kicked in. And when things don't go right, when the governors aren't working at all, you get blackout. And this is an example, just fantastic. And look what they accept as nominal. It's amazing, I mean, it really is usually 50 hertz, but I mean, it's amazing how robust it is compared to the US. Okay, so we need responsive regulation. And again, given the state-of-the-art of distributed control, there's no science for it at all. It's a miracle. And I'm going to explain to you how it's not that surprising. Basically, the way this has been designed, it makes it easy to analyze. So there's no theory for, say, optimal distributed control. But the hack that power systems engineers came up with makes it easy to analyze. That's what's beautiful, and that's what you have to do. You've got such a complex system, you have to design it so it's analyzable. That's sort of a mantra, I think, in complex systems. And that's what's happened in the communication systems. At first sight, it's insanely complex, but TCP/IP is this distributed protocol that makes it analyzable. It has no optimality features. It's a hack, and it makes a really complex system simple. At least in behavior. So here's where we were last time. So now the equations come in. So let's go through this a little more slowly. So I came up with, so in terms of secondary control, okay, so restoring frequency to its nominal behavior, and in terms of using all the resources available, supercapacitors, batteries, the demand response ideas we'll be developing, generators, in order to get any insight in grid level control, you need a macro model. Okay, and that's why I started to. I was just giving you a plausibility argument in the last lectures, last lecture, and this was the formula we came up to just as people were starting to push in and try to kick us out of the room. So I won't derive this again, but go back and you've got the notes. I uploaded them online, and there was a transfer function here in terms of this ugly thing here, which was the non-frequency sensitive load change in load. All right, so if that goes up, you know, then there's a power mismatch. If it suddenly went up, more typically this represents a drop in load, a generation. The generator goes out. It's just like load going up. Okay, that's why there's a minus sign there. And we found there's a 0 in the transfer function from here to here. That's always going to happen, and not here. And I wrote 1 there. I guess that's a typo. I think I had a constant there, an M. I called it M last time, so typo. I'll try to remember to correct that. And A of S, in the end, I came up with a hack for that. I pretended it was second order, which is a reasonable approximation. We'll see. Okay, so the beautiful thing is that's the Laplace transform of the signal that's sent by the balancing authority. So, PJM or Florida Power and Light or whoever, GRU is going to send that signal to every generator, maybe scaled for depending on each generator, and that's an input that's going to be change their mechanical power, and thereby, that's broadcast to everybody, and then changes the grid frequency, right? Now so that's a big, that is the major architecture of the secondary control that we'll be talking about. You know, the grid operator now can play God and send a signal to all the generators. So they're all doing their little thing, looking at the frequency, local frequency, but they're also looking at that signal which is sent from 1,000 miles away maybe, which is manipulating the behavior as well, but on a slower time scale, not in the order of seconds like primary control, on the order of minutes. All right? So we'll have fun with this. Now, again, so I argued that there were approximately this, if you take another course, you'll see there's pretty good arguments that you can approximate by a second-order polynomial. So that's a second-order transfer function. So there are 2 poles. And approximation gave this, where TG was an approximation for a first-order term. M was the sum of all the inertia constants. And this is what you learn in a control course, this representation. This is a way of describing a second-order polynomial, So this zeta term that appears here is called the damping ratio, and it's only if zeta is less than 1 that this term is important here. That has meaning, and then it's called the natural frequency, and I'll explain where that comes about here. We really need to understand. It really is helpful to understand that. I'll explain it before we get to control. Okay. Now. All right, any questions? Was that all clear? Like I said, it was the most boring lecture ever, but we need it. Last lecture. So there it is. So just tearing this apart again. If you go back, you can work these out. You can. I gave you a formula for omega n squared. I gave you the 2 zeta omega n. They're in your notes. All right, and they're horrible expressions. And the omega n squared part is this times this. It's actually just B plus D. And if you recall, B was the summation of 1 over Ri. Where Ri were those Drew parameters. And there's the natural frequency. And that's where you think, that's where we're going to see, when zeta is less than 1, that's when you expect to have big overshoots. And so you might think that's what's going on. Where am I? Yeah, I'll get back to that. So in the case where, let me explain this diagram. In the case where zeta is less than 1, this is what the 2 poles look like. They're complex. So that's why zeta less than 1 is important. I mean, these both have to be, everything has to be positive for the poles to be in the left half plane, which you all remember is necessary for stability. Even though in my pole, you said you knew nothing, you better know that you need poles in the left half plane for stability. Okay? Bounded input, bounded output stability. You better remember that. But zeta less than 1 is when you get complex poles. And you have this nice interpretation that omega n is the distance of that pole to the origin, and zeta is equal to the sine of theta. All right. So if that angle is 0, that's when zeta is 0. And that's bad news. You get a pair of poles on the complex axis. And that's not stable. So zeta is 0 is, you'd put it, a step response would result in oscillatory behavior forever. Yeah, okay? So you don't want zeta too small. And if zeta is very small, it's almost like that. It's almost like you have a pole on the imaginary axis. And so a little jolt will cause big oscillations. And so these big swings in frequency would be a cause of zeta being close to 0 or something. It's not. I'll explain that in a minute. There's big overshoot, but it's not because zeta is small. All right, well, let's keep going. So here's what happens in real life. This is a simulation, but it's a really high fidelity simulation of what happens in real life. So the WEC, the Western Energy, blah, 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 I don't remember. Doesn't matter. Don't look it up. Don't get out your phone. But anyway, so it's a simulation of Western US. It's examples, again, of what happens when you have a lot of wind generation and low inertia or not. And you get different swings in frequency, not that different, depending on the mix of wind generation and traditional generation. Now, what's happening in this plot? Again, this thing that with this awful notation, non-frequency sensitive load, which could also be just a generation outage, again, okay? So it's either a load that's not frequency sensitive or a generation. It goes along, and at time, that's 10 seconds, at time 1 second, I don't know. I'll just call it T naught. It dropped some amount. Oh, no, it jumped up. That's right. A generator dropped, which is equivalent to virtual load increasing. All right? So that's called a step input. All right? Now, we know that the transfer function from that signal to deviation in frequency, so ignore that for a moment, because that's going to be at a much slower time scales. All right? It's got a minus sign in front. All right? And so basically, if you look at delta omega of t, which is at 0, so that's not showing delta omega, that's showing omega itself. So subtract off 60 and you'll start off at 0. And what you're seeing is that at this point, first of all, do you notice the corner? That's indicative of a 0. It's a perfectly consistent with a second order system that has 1, 0, and 2 poles. Exactly what you'd expect. It means relative degree 1. So a jump in the input resulting in a corner, still continuity but a corner, means you've got one more pole than 0. So the degree of the numerator is 1 less than the degree of the denominator. All right, so I'll let you Google that. That's a degree 1. Okay, and then and it goes down. Now step responses usually go up. it goes down because of the minus sign. So this is a negative step response. Negative, again, there's a minus sign there. So that's a transfer function. That's it. So that's what's really cool, is that generators go out all the time. So we get to observe step responses all the time. And that, any control engineer looks at that and says, that's a second order system. I can fit a second order model to this. And it's for control design, it's perfect. All right?
There's a typo in that.
Oh, is there? Oh, that's right. Oh, is there? Yeah, we'll talk about that later. Yeah. Okay. There's a typo here, which yeah, that's right. Anyway, I'll broadcast a correction later. It's no big deal. So anyway, this is a high fidelity simulation of the Western U.S. You can see the same thing happening from real life. I've shown you a million examples of this from real life. And here's an example of a professor in Texas, Ross Baldick, who's a friend, he's the main guy for power, in Texas, really, who did basically what we did. He basically computed this, as a lot of people have. I mean, this is an old thing to do. And by the way, I've left things out. I mean, there aren't just, the big spinning machines aren't just generators. There are loads that are big spinning machines. So you have to throw those in as well. All right. But basically, in this paper, there's no link here. There should be. I'll put one in. But in this paper, he just went through and he did an inventory of inertia and so forth, and he was able to get different models for different operating conditions. And I know this is the Western U.S. and that's Texas, but anywhere you look in the U.S., you'll see similar, large regions, you'll see similar behavior. You get the same sort of negative step response. But this is not recovering, it's not going up. This is flat. And you know what the difference is between the two? Yeah, you have to shut up. It's actually taken out of a paper that we So this is a high fidelity simulation where they took everything into account, including secondary control. So if I plotted this long enough, after an hour or so, it would get back to 60 hertz. But this simulation is without the secondary control. It's just looking at the grid dynamics. And so it goes off to a final, delta omega steady state. And that's what it is. Okay. But this is just a second order system, and actually zeta is bigger than 1, as I recall. It's not underdamped at all.
So after repeated shocks with those dashed lines keep settling into lower and lower.
Well, yeah. We know that, right? We know that the steady state is, so delta omega infinity. The steady state, you have a formula, right? It's equal to minus delta P, L, and F infinity divided by, do you remember? It was D plus the sum of the one. Yeah, I think that's the formula, and that's what we got. So so the larger this is, the more it'll sink, and that's scary. Yeah. So you lose like 1 gigawatt plant, or the 2 gigawatt plant that we saw in it was Indiana. Holy shit! That's amazing. That's 5% of the load in the Midwest. So. All right, cool. So anyway, so the thing is, it matches reality. I know these are both simulations, but you've seen real plots as well. It looks like a step response. So we're in good shape. And so this is what the grid operator needs. So if you know anything about control, if you're going to build a flight control system for an airplane, and somebody gave you a model they used for simulation, you would laugh in their faces. It would be so complex. It would be a partial differential equation of 50th order in 100 dimensions. And you'd say, what the hell am I going to do with that? What you do for control design is you say, give me a second order model. I don't mind if it's 10 dimensions, but give me something simple. I can design a control system based on the simple model, And then you can do numerical experiments on your fancy PDE simulator. You can't do design based on a complex model. And that's the hardest sell of this field. People will not accept that. People who don't know about control theory, you go and try to talk to them about that. I need a simple model for design. They won't let you talk to them. It's so frustrating. In so many different fields. They don't understand the abstraction, that you need a simplified caricature of reality to get insight and get initial control strategies. And later on, when you do the simulation, sometimes you find this issues, like in Droop, this weird deadband. So you actually don't do anything with Droop, really, until the frequency gets out of a deadband. It's not really linear. You only kick in that integral control when the frequency goes out of some small deadband. And I guess there was some chattering that they saw, and so they put in the deadband to resolve that. And you wouldn't get that from this model. You need to go and get a high fidelity simulator to do that. All right. Okay, so this is how you would do a design. And the thing is, for secondary control, the dynamics are so simple, you can get away with murder, I really believe. I think it's much, people talk about much slower time scales. I don't think the dynamic issues are as critical as they are in these time scales of seconds, where you can just blow up like that in a few seconds. But on the order of minutes, I think really simple models can be used. It's my conjecture, okay? I might be proven wrong someday, but most people in the power systems community agree with that. But it's who knows? The thing is, who knows what's going to happen when we make so many changes to the grid? I have intuition from reading books and seeing plots like this based on the current grid. And what if we got rid of every traditional generator? We'd be, we don't know. So I could have false intuition, but if we don't make major changes, what I'm saying, I'm sure is true. All right, what's next? First of all, let me explain this. I'm going to kill this now. Any questions on this? So, okay, so it might be ambitious, but I want to do a few things today. First I want to just explain to you about dynamics of simple models, just to get some insight. And then I think I can do it. I think in 1 hour I can teach you everything you want to know about classical control. And if I'm wrong, we'll go a little longer. But I think the main idea is you can explain really clearly in 45 minutes. So that's a normalized transfer function like this. So no zeros, and I've made a change here. I've made a normalization. And why would I put this funny number on the top? Any guess?
Constant m?
Well, not m, but there was some funny number here before. I had a b, which I could write down. Before, it had nothing to do with this. They weren't related in any way. The reason for this is, note when I put an s equals 0, I get 1. So there's a DC gain of 1. So it's just a normalization so that if you put in a step input, the steady state will be 1. Okay? So if you look at H and you have some input-output behavior like this, I'm going to keep that in there. Okay, just remember that often I'm going to be thinking about the case where zeta is less than 1, which means the poles are complex, and we can interpret this. Yeah, this nice geometry. So if I put in if U of t is a step input, if you put a step input to a linear system like this, you get what's called a step response. And I mean, a lot of you only saw discrete time. I don't know if you saw this, but so Y of t is called a step response. So it's a nice stable system. You're putting in 0, you get 0 out, and then suddenly you jump up the input to 1. This is relative degree 2 because there's 2 poles and no zeros. And so you don't get a corner, you get this smooth behavior. And this is what you'd see if zeta is really small. You know, that might be zeta equals 0.1, something like that. And what's this value? What happens when you put a DC input into a, 1. The DC gain is 1. So that's 1. Okay? So that would be, that's one example. And here's another example you might see. And it will never quite reaches it. But
I want to say at the steady state, the whole waveform will converge to 1, which is the DC gain. That's the whole interpretation of a transfer function. If I put j omega here for any omega, it tells me the gain at that frequency. And so 0 is DC, j times 0, and 0 is DC. So I won't review that. So 1 is where, say, zeta equals 0.1, and 2 might be zeta equals 2, where the poles are actually real, and you might see something like that, where there's a slow, very slow upwards. All right. Okay, so that's something to know. And again, if I don't have room to put it in, but if zeta was 0, it would do this, and it would just be a sine wave eventually. It would converge to a sinusoidal behavior if zeta was 0. If zeta was 0, you'd have poles there and there. So it would just be like a perfect slinky. Pump it, a frictionless slinky. Just hold it and boing, give it a little kick, and it goes boing its natural frequency forever. All right, so why do we see this here? So that's the case of no zeros. What if we had zeros? Let's give it another name. Let's call it G of S. I don't know. Okay, so we found that when we got the response from disturbance to frequency deviation, we had this behavior. We had a state. We had a constant here which was positive, which means we have a 0 in the left half plane. Okay, so now we've got exactly the same picture, but we plug in a 0. when you look at it like that, you say, what the hell can I say? You could say some things. I mean, if tau is very, very small, you can imagine it's almost like that's not there. Well, if tau is very, very small, it's like the zero is not there, but way out in infinity, it's sort of like not there. But if tau is big, that means the zero is more close to where all the other action is. Then that's very different. But the thing is that let's give this a different name. Do you mind if I change this? So this is the response when there is no zero. And now let's look at the response when there is a zero. So you all tell me, how is y related to u? I mean to y not. Why not? We know how y is related to u. Y in the Laplace transform domain is g of s times u of s, which is 1 plus tau s times h of s times u of s, right? And you notice I flip these around, but they commute. So how is y related to y not? Well, forget that. I mean, let's do this first. Yeah. Let's do how is y of s related to y not of s? Is it obvious? I hope. I'm just checking to see if you're awake. I mean. Just by the definition of transfer functions, y naught of s is h times u of s, right? So there's a right there. So yes, absolutely. So y of s is equal to 1 plus tau s times y naught of s. And then, as Joel points out, we can take inverse Laplace transforms. And remember that multiplying by s is differentiation. And that's where you have it. You see, tau is positive, and you're getting the original response, but you're adding the derivative. And so if tau is big, then even though the nominal behavior was like that, you're adding on the slope, and you can end up getting some big overshoot anyway. So you could have a situation like this. Where y naught of t is perfectly well behaved. Its slope is pretty much zero out here, so that doesn't play any role. And the slope is zero here, so that doesn't play any role here. But then it's got something here, so if tau is large, you could get something like this, where it's close here, but then shoots upwards, and then comes back together. I'm sorry, I should have brought Neil's colored chalk, but I hope it's clear. So, the adding on this term is what creates overshoot. And it puzzles me that they can't fix it by design. So their design of the governor and all of that introduces a zero in the grid dynamics overall. They did it. You'd think you could come with a new governor design to get rid of it. And it just occurred to me during last lecture, actually, or as preparing last lecture. And I have to think about that more. I'm trying to work on a homework assignment so you can do it. get rid of the zero by design, and it would help somewhat, But anyway, so that's the first thing. Okay, so you all with me? So this is the reason for the big undershoot. Really, is just the zeros, because when you actually look at the models they come up with, it's not that they get poles near the imaginary axis. That would be really scary. That would mean you have stability issues. That if something goes wrong,
those poles might end up in the wrong, in the right half plane. It's unstable. You want those poles away from the imaginary axis, and they're designed for that. Okay. All right. So, no questions? Deep breath. I erased all those? Yes, Neil.
I forgot that. So you said you defined Z as sine of theta?
Zeta, that's what, it's just magic, it turns out to be true. If zeta is less than 1, you can actually, just using the quadratic formula, find the roots of this polynomial. You'll find they have this geometric interpretation, where that's omega n. And if you define that as theta, the zeta appearing there turns out to be exactly sine of theta.
How do you get a Z greater than 1? What is that?
Oh, that doesn't have any meaning.
Oh, okay.
Yeah. I'm saying that omega n only has a reasonable interpretation if zeta is less than 1. If zeta is bigger than 1, that's called the overdamped case, and there's no interpretation anymore. It's yeah.
This plot, the curve that is above 1 is y of t, right?
Yeah, because of this additional term here.
Exactly. So the term at the bottom, which is y naught.
Yeah,
Okay.
yeah, that's right. Yeah, so even if you had an overdamped response, you could still possibly, depends on what tau is. So if tau is very, very small, then they'd be almost the same, you know. But tau is not very small in the grid. You know, it's in the grid models, at least that I've seen for big regions like ERCOT or yeah. Okay. All right. So that would be the first 2 weeks of a first year control course. They spent a lot of time giving examples of DC motors and playing around with dynamics, and you'd look at other you'd look at state space models based on this, things like that. Yeah.
In terms of equation,
Yeah.
what is y naught t?
Oh no, nothing. I mean, right there. I'm just saying. Suppose we first start off with a system. The differential equation. I mean, we know that, right?
Yeah.
Oh, come on.
Still pressure was not that.
Okay. No, it's actually given right there. But what the hell? Sure, why not? This takes a second. So forget about why not. Let's just go all the way to y. Oops. Yeah. Oh, that's right. Okay, so if I unravel that equation, I'll get that equation, because this was, I won't write it down again, but this equation is exactly the same as what we had before.
Yeah.
Right, and so then you go through and you again do the same thing. You take inverse Laplace transforms, and you get y double dot plus 2 zeta omega n y dot plus omega n squared y equals omega n squared times u plus tau times u dot. And that's a good indication of what's going on. I mean, if you use a step, then u dot's a direct delta function, and you're hammering this thing. And that's why, and look at the mistake here. Look, mistake. When you have, I remember I was screaming, relative degree 1 means you have a corner. It's just a good way to get intuition about a system. The corner there could be interpreted as this. The impact is generalized function here. That's you've got a direct delta function for you, if you use a step. All right, so that's what we're talking about. All right.
This is now y of t, right?
What's that?
This is now y of
This equation
if you go back and look at the definition of H of S, you know, it was a
That's it.
well, maybe what it was. We had a four. I just erased it. I'm going to write it down again. I defined this to be omega n squared divided by blah, blah, blah.
Yeah, yeah.
And all I did was I wrote it out before this was in the bottom here. And that gave you H of S, right? So, yeah, so you should go back and study that. Because I don't want to put the equations back out. But these two equations are identical. Okay. All right. All of classical control. So let's do it. I'll write down a picture and then we'll take a break. So here's a standard architecture. Okay. Okay, so we have a plant G sub P, which could be like the G over there, or it could be something else. Like this would be like the grid transfer function, something like that. All right? And we have a reference signal which is desired behavior, you know. So for example, for the grid, 60 hertz, you know, something boring like that. You know, we're not going to, nobody's playing around saying, let's be India, let's be the US, let's be India. Nobody's ramping up and down frequency. So, you know, we usually would have regulation problems, and that's it. And I just realized things aren't out of whack there. And there's some way of making decisions I'll put this back in a second. So this is just one architecture, okay? That you take this, and what you do is you take an error signal. Take an error signal, put it through a filter, and that defines your control, and which goes into a plant, a physical system, and gives the output. So this here is in, you know, typically on a computer, and that is physical reality. Computer reality. And this is why it's so hard to take control course. Same thing happens in communications. You can't tell physics from what's on a board, you know. It's so hard to see. But this one architecture based on error feedback you take what you want minus what you measure, and that defines the error, and you put it to the compensator, right? So that's step one. And it's a standard architecture mainly because it's really convenient in teaching control just to have one architecture and tear it apart, you know? So if we actually go back and look at the architecture for the governor, it was a bit funky, you know? It did look like this from the operator, the grid operator, to the valve input. If you go back and look at it, but anyway, but there are other architectures, and and there's a lot to say about this. But so let me go a little further before we break. First of all, just think this is obvious. What you would do something like this. I mean, imagine if this is a cruise control, okay, and you want to go 60 miles an hour, you know. So R is 60 miles an hour, right? And then you take a measurement; it's only 55 miles an hour. So 60 minus 5 55 is 5, a positive number, and basically this is going to have some positivity thing. Increase your pressure on the gas. Going too slow, hit the gas. Going too fast, let up. Now that assumes there's some positivity here, that when the error is positive, that's positive, which is what we'll assume in a sense. But even better than that is this. I mean, in the Laplace domain, y is equal to g. Let's call this whole thing g. So basically, to get y, I take this transfer function gp, I multiply it by gc times the error, and the error, again, is r minus y. Right? The error is r minus y. And then you can unravel this. And bring things to the other side. And then divide. And the problem is solved. If my goal is to make e go to 0, right? I want the output that I'm measuring to be equal to the reference signal. Problem solved, right? How do you make that 1? There's only one way to do it. How do you make this 1? There's only one solution. What?
G is really big.
Yeah, G is infinity. Yeah, so G equals infinity. Done. Okay? So if we were writing like code, I mean, this is the kind of thing that you would start off with. You'd say, well, if I want to achieve this goal, in some sense, I need infinite gain. And now, you don't. For this architecture, that's what you would need. If you want the error to be exactly 0, you would need that. Of course, we could have a completely different architecture. We could forget feedback. We could just let this be 1 over GP, and then forget about feedback. But then we would have to know the plant exactly, Right. So if the goal of control is to know very little about the plant, and this silly thing I'm saying here suggests I don't need to know much at all, We'll take a break here, but of course, of course, I could relax this. I could say 10 million, but what's the problem? What am I ignoring in this analysis? So why can't I just say, if I take g equals 1 million, I'll get 1 million over 1 million plus 1. All of you would agree that's close enough to 1. Oh, it's not. Yeah, it is. For the grid, I only... What's wrong with that? What am I leaving out? It has to do with your question.
Error.
It has to do with this. That there is a physical reality. I mean, there's a model of reality anyway. No, it's just the fact that this is a dynamical system. It's not a bunch of algebra, and it might not be stable. And so, what you need is high gain. For both tracking and disturbance rejection as well. If I had, the wind coming in here as well, if I had disturbances coming there and there, from wind, from people fiddling with things and all sorts of stuff, if I wanted to kill off those disturbances, I could show you we'll get the same thing. We need G to be huge. But that's only number 1. We need stability. Not just stability, not like what you learned about signals and systems, but real robustness, that even if my model is completely nuts, it's still stable. I want my model to be very unimportant. It would be stable for a wide class of, even with huge modeling errors. And so it's so cool. The beautiful thing about the frequency domain is it's so obvious how to do this. And so, all right. So we'll come back in 5 minutes, and in 40 minutes, we'll completely be done with the first half of classical control. All right. So let's take a break now. First, pretend one input is 0 and look at the response from 1, and then you can pretend the other input is 0 and look at its response, and the total response is the sum. So I'm not going to review that. But if you just look at the response from d to y, it's 1 over 1 plus g, so you get the same exact conclusion. Oh, I should have waited 1 more minute. Sorry. I'll back up. So, disturbances. You can model them in various ways. They can be summed in there, summed in there, summed in there. They could be summed in somehow in the middle of the plant. This is just one example, because no matter what you do, you get the same conclusion. So if you could model wind disturbances or something like that in this way, then you could do the same algebra, and you get y over d is 1 over 1 plus g. And you get the same conclusion that you need g equals infinity means you get rid of the disturbance. So if you really were so naive to think you could make this identically 0, you would say that you have to have infinite gain. All right, but that's ridiculous. So I should say the disturbance anywhere here in the physical reality. I mean, disturbances here means somebody's messing with your air signal. That doesn't. No, that's a cybersecurity issue. Forget that. Any disturbance going anywhere here, you'll find the same conclusion. All right. So it's not stable. So this is never stable. All physical systems have limitations on their frequency response. And if you have not infinity, but if you have very high gain, any physical system make the gain high enough, it's going to act funky. Something's going to break, or it's going to be unstable. So what's the conclusion? That's the main idea in classical control. So to achieve these two goals, you can't achieve this. You have to relax your goal. You have to have, the goal, I'm sorry. These are now two goals. We want tracking disturbance rejection, and we want stability and robustness. To achieve this, we have to relax what we mean by this and just say, in some frequency range, we want really good tracking. So this to relax our goals. So like we have this transfer function I'm sorry, I'm going to have to write Bode plots. All right. So E was, remember, E was R minus Y. We want this transfer function to be really small, say really tiny, say minus 100 dBs maybe, I don't know, in some frequency range. And outside of that range, it can get big, we don't care. And this makes complete sense. We're not trying, the grid operator is not trying to send reference signals at a millisecond, on timescales of milliseconds, on timescales of minutes. There's a natural range of frequencies where you want good tracking, and the rest, It's just, there'll be other passive devices. Besides governors, there'll be large capacitors, things like that. And just natural inertia in the system, which will kill off the high frequency stuff anyway. It'll disappear on its own. So high gain and low frequencies. So that, I mean, that's what we need, right? I mean, where is it? Oh, shite. Oh, I didn't write it down, did I? I'm sorry, exercise. Yeah, I gave you y over r. I didn't give you e over r. But otherwise it would be awful. I'd have to say 0 dBs, and if I put a y here, it'd be harder. It'd be less intuitive. If you looked at the transfer function from the error, the reference to the error, you just ended up with 1 over 1 plus g. Okay.
We had y over here, didn't we?
Well, that was y over r is g over 1 plus g. And e over r is equal to r minus y over r is equal to 1 minus y over r, right?
Right.
And that's equal to 1 over 1 plus g. I'll let you do the algebra. All right. This is a more convenient thing to look at. And I'll keep that happy face done. Because if this is our goal, then it's not hard at all to make G massive in this frequency range and then just forget about it outside of that frequency range. And classical control for single input, single output systems, this is most of the content. It's a beautiful subject. Especially when you get to unstable systems, it gets really stable, subtle. But we're talking about a system that's not nominally stable, and so you can really quickly get insight on what to do. All right. So what I'm going to do is I'm going to give you an example of a bad design, and I want you all to tell me why it's bad. I'll give some hints, and if you've taken a lot of controls, shut up for a while, okay? Now, typically you're not going to see this because it's really, this would mean you have a big static, this being constant for a long time, and then, it's not what you typically see in practice. Typically what we see in practice is huge values at low frequencies, and then maybe something funky happens where it flattens out, and then it goes down, and maybe it goes down really fast. So that's a magnitude plot in dBs. And remember dB plots, right? I'm not going to remind you, but there's a logarithmic scale here as well. Okay, so, like this is 10 to the minus 10th, that is 10 to the minus 11th, that's 10 to the minus 9, And so going way over here is DC. So you have really high gain at DC, and then it comes down. All right? So there's the magnitude. Now the phase is important. And I'll show you what typically happens is you'll have phase equals minus 90 degrees here. We'll see that is what happens in almost every application where regulation is the goal. And then it typically decays. Now this is a bit scary. This is a really scary system. Now, where the phase goes like this. Now, in real life, you can't measure things like this because the magnitude here is already 10 to the minus 10. I challenge you to look at a sine wave with magnitude 10 to the minus 10 when it's normally is 1, magnitude 1, and measure its phase. So these things, this is not even measurable, so it's not even reality. But let's say that's minus 90. Let's say that this is minus 180. And let's pick some other stipulations. Let's put a number here. It really is, it's flashing. All right, so we got some life here. Okay. So the danger is that it looks like maybe there's a pole at j omega naught, you know. Yeah. Right? It's possible because 1 plus a negative number can potentially be 0, and that's a pole. So the only way, you know, a pole means that g is minus 1. Right? And so g could be minus 1. And there's the red flag. I mean, it's hard to see here. It looks like we just missed it, you know, but we don't know. We came up with this transfer function based on, you know, based on the stupid arguments I gave in lecture, and then based on some least squares. I mean, so the magnitude, the question mark there, and the answer is yes, if the magnitude of g of j omega naught in dBs equals 0, because, you know, that's a log in dB, so being 0 is the same as unity. And it's not, but holy shit, according to this plot, it looks like it could be very small. That's called the gain margin. You know, and basically, if that's very, very small, then a very small bit of modeling error, and you actually have a pole on the complex plane. Okay? And you know, move it a little more, you're going to get poles in the right half plane. You'll have instability. This is a really big, this is a central concept of classical control. It's for understanding that boundary, see? I mean, why are we obsessed with the imaginary axis is because poles in the left half plane are stable. One pole in the right half plane, it's unstable. Right? This is the wall between stable and unstable. Right? And so you want to protect that wall, right? You want to build that wall and protect it. You know, I'm not quoting Donald Trump. All right. And so anyway, so that's called the gain margin. The other thing is called the phase margin. You go back here, let's call it omega 1. So we go way over here at omega 1. That's where the magnitude actually is, you know, model exactly unity or 0 dBs. And you go down here, and how far you are from minus 180. That's called the phase margin. And in this example, it looks like I've got lots of phase margins. That's 90 degrees. That's 180 degrees. My God, you don't see that in real life. You know, it means I could have incredible uncertainty in the phase and still have stability. I won't have this issue of a pole. You know, and you know, and the thing is that why can I be so flippant? It's because of the fact that if you tell me the system's stable, perturbations, it'll still be stable. If I perturb it, the poles will change. So the poles are stability means the poles in the left half plane. If I perturb it, they'll move around. They'll move around. If I perturb it more, they'll move more. If I continue to move it, at some point, the pole, one pole, say, will go from the left half plane to the right half plane. But if I do that perturbation continuously, there's a wall there. It has to go hit this wall, you know, right? And so as I perturb, I can, if I say, you tell me it's stable, I can drag this all around continuously. And as long as I don't ever have this horrible condition happen, where the magnitude in dBs is 0 and the phase is minus 180, I know my perturbations won't have destabilized the system. It's a beautiful, beautiful way of thinking. And this could be an infinite dimensional system. It could be a PDE, and the logic still goes through. It would have to be second order. All right? Oh, the last 10 minutes were really core to everything. I mean, I don't know. That you want that to be big. You want a big gain margin, and you want a big phase margin, especially if there's uncertainty in the plant dynamics, which is typical in the power grid. You know. So, one caveat, I just realized this one thing. Well, it doesn't matter. I'm going to say this. Okay, so remember, the goal was to make G big in low frequencies. The plant is something we can't do much about, so it's the compensator we're going to crank up. And what's a transfer function that's big in low frequencies? So low frequencies means, for example, DC. Can you give me a transfer function that's infinity at DC? I don't know. Yeah, 1 over s. So if I want infinity, there you have it. You know, at DC I have infinity. So having infinite gain at DC is a piece of cake. But we can put a gain in front of that. And I'll call it Ki for integral gain. Okay? But I can always add other stuff as well. And I could add more terms. Should I? Oh, I guess I will. It's almost never done. This is called a PID compensator. It's really rare to keep this last part in. So PI is more common in practice. And the reason for that is that, remember what this means. You know, this is a filter that takes E, and you filter the error signal to get U. And so this says that if you take inverse Laplace transforms, dividing by S is integration. Let's do this first. Since it's PID, let's do the proportional part first. So it's just a gain times E of t. And the I, then it's Ki times the integral. And then KD, so multiplying by S, as I mentioned before, is this differentiation. And you can imagine in a lot of cases this is noisy, and differentiating it causes all sorts of problems. So there's much more clever ways. Now this has a role for stability, but there's much better ways to deal with that. So we're not going to talk about that in this class. So we're going to just look at PI compensators in this course, and that's all that's ever looked at in the power industry. It's amazing. Yeah.
No, the differentiation. I mean, the high frequency noise can be like increased, right?
No, that's what I'm saying. Yeah, if E was a triangle wave, and this would have also. I mean, not triangle wave. If E had discontinuities, you get infinite values. I mean, it's just and noise gets amplified. So there's better ways to do this. But that's a control course, and it doesn't arise in this subject. So in power systems, they are so risk averse. The models are so uncertain that they really are conservative. And you only need this part if you're trying to be more aggressive. Something like this you would have in high-performance aircraft, where you're really trying to just make the bandwidth huge. So they go for lower bandwidth in power systems because of so much uncertainty. All right. So let's do it. Cool. Okay, so our grid transfer function, let's do it. Let's control the grid. We have a grid transfer function, Forget the minus signs, we'll get rid of those, okay? Remember I introduced an EW, so I wouldn't have to have that minus sign, so throw away the minus signs. If you look at our model, it is really, boring as hell. So this, I don't know what it is, I don't care. Because I'm going to annihilate it with this monster. As long as this is not zero, as long as this is minus infinity, which would be 0, I'm happy because I'm gonna kill it with this. Right? And if you look at the phase, it's 0. It's just 0. So in low frequencies, it acts like a pass, like there's nothing. I mean, push it, it moves. Frictionless, nothing. There's no dynamics. And then the dynamics kick in, and the phase drops, and pretty fast. And you've got your own prejudices, which we'll correct. It goes down to actually, in our model, minus 180. But forget that. I'll put a dashed line there. Remember we ignored the valve dynamics? Remember we ignored blah, 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 blah? If we put those all in, it would start to go down. And it would settle off at minus, minus 720 or something, So, so our model was reasonable up to here, and that's it. Now, it turns out what's really lovely is that this time scale is like if you think about the frequencies in this range, they're like sinusoids with period of a few seconds, So let's say around 10 seconds maybe or something. I mean, maybe 5 seconds, something like that, right? So there's a lot of uncertainty here. I don't know exactly where this hump is. I don't know exactly how big it is. But it's on these faster time scales that luckily I don't care. I'm just gonna run away from that, So there's uncertainty here. And there's phase lag. Phase lag meaning negative phase. And it's negative phase that scares me. So we'll just stay away. And that's what's done today in the grid. And that's what's done in every application. If you've got a lot of uncertainty in dynamics, you cut it off. So remember, I can crush the gain if I want to. This is GP, not, I can play around. All right. I have to erase that. I want to put this all in one thing. All right, so yeah, I wanted to do the whole design on one blackboard. So I've got my G sub P, which we created through a thought experiment and validated by looking at any fault in the grid. You can see a step response, which is consistent with this model. Where it's basically a static gain up until frequency band where there's a lot of uncertainty. So we've got that. And so now we can stabilize this monster. So we want, we'll use a PI compensator, and I'll now give you a plot. Okay, so remember from now on, that's not an example. This is us. This is PJM, or ERCOT, or anybody you want. This is it. We're going to use PI compensators. That's my definition of a compensator for the next weeks. So what do we want? This gain, whatever it is, it's not big enough. I want it to be big. I want it to be really big. And I do that by throwing in this pole at the origin. And so when, remember, we're looking at G of J omega, where omega goes from 0 to infinity. We never really get to 0 because it's a log plot. If the frequency is very small, this thing totally dominates. And this is insignificant compared to it. So it's just, if you actually plot it, it's really just a straight line. That's for low frequencies. But when S, which is J omega, is very large, this goes to 0, and this dominates. And so you end up getting just a constant. I never define dBs. I'm doing it now. So this will eventually settle down to the magnitude of Kp and dBs. And this corner is the middle frequency is a place where these are commensurate, which is actually minus, this over this, the ratio. It's K. Oh, no, but this is a positive frequencies. It's Ki over Kp. Yes. And you're right. I should say that. Yeah. So when you look at the poles and zeros of a PI compensator, you're introducing a pole at the origin, and you can check it out. You're introducing a 0 at exactly minus that location. So it's the 0 is at minus Ki over Kp. Right. And in some control applications, the location of 0 is really important. But here, we're going to see it's not that important, maybe. We'll see. And that looks bad, though. God, you guys have all written this down? I did a design just now without knowing it. And it's going to be a really crappy design. And you guys can all tell me why. It's okay. Okay, so the same arguments go for the phase. If you put in a S equals J omega, 1 over J is minus J, and the phase of minus J is minus 90 degrees. And this is huge compared to that, so you get a phase of minus 90 degrees. And you can come up with very, very nice heuristics. and there you're done. So this isn't a good design. No, I don't like it. I don't like it. But let's think about why. Yeah, we'll definitely need another lecture for this, but all right. So. So I said that there's a lot of uncertainty here. I'm definitely going to compress the gain a lot. I don't want to accentuate the gain a lot here. Well, I won't, I guess, because the magnitude is decreasing. I guess I can erase all this. Okay, so when you look at the products that we care about, and luckily when you look at that, you look at the sum of the two. And so what I've actually done is I've made it, instead of being flat here, I've made it decrease. And then I've made it flat for a long time, because that's just the natural dynamics now, and it comes down. All right? And then I've got the phase. Which I said is minus 90, and then it comes up. It's going to be flat a while, because the phase here is 0 and the phase here is 0, but then it's going to come crashing downwards. All right, so why do I not like this design? I could have maybe done better. And the question is, remember I was obsessed, say, let's just look at where the magnitude is 1. So remember, this was a critical point. If the magnitude is 1 and the phase is minus 180, I'm in deep doo-doo. So it could be that it's omega 1 is there. But that means that's 0. That means the magnitude is 0 all the way around there. That would be really stupid, because the magnitude would be basically, I wouldn't know where the crossover frequency is. It could be anywhere here. So that would be idiotic. All right, because it could, who knows, maybe it would get into this region. Okay, so if I did a good design, my omega 1 is probably over here. And that's so that I can suppress things, you know, where the, and especially suppress that resonance, where I know nothing about the system. So this is by design. That's going to be 0 dBs. So I know that for stability and robustness, right over here, that's minus 90. Well, it's not until here. So that was an important thing. I mean, I don't know where this is exactly. I want to suppress this. And so I know that I'm going to design this so that omega 1 is over here. All right? So why is it a crappy design? So remember, this is 0. Well, I've got high gain. You know, it's blowing up, right? I mean, so anytime you use a PI compensator, you've got infinite gain at DC. But you're on the right track, because this keeps going, right? I mean, I can't go forever. Or maybe it's a log scale, so that's 10 to the minus 10, 10 to the minus 11, 10 to the minus 12, 10 to the minus 13, 10 to the minus 14, you know. And that slope is linear, so it goes to infinity. But why am I wasting all this bandwidth? You know, I mean, I'm going to have high gain at very, very low frequencies, and I could do a better design. So we'll do a better design next time. But so I've got stability with this design, but it's a very low region where I have high gain, very, very, very low frequencies. So we need so higher bandwidth means a larger region of my error is 0. So here it's going to be only when the gain is large. Well, that's 0 dBs. It's a frequency range way over here. And I mean, I don't know what these units are, but it looks like it's really far from. I could do much better. All right. So we'll think about how to get a better design next time. So next lecture, I'll spend maybe 20 minutes more, half an hour reviewing to do this, and then we're done. I just have to give you some homework to play with this yourselves. Questions? No? Okay. So it can be done. Classical control in 40 minutes. I mean, not without homework. You gotta do a problem. So I'll cook something up. Cool. Until next time. Oh, I know. Oh, you all look expectant.